Welcome to my channel. Today I am going to explain the next topic in the data structure subject, that is AVL tree. First we will see what is tree. The collection of nodes and edges are called tree. The tree is denoted by the letter that is T, and here one tree is invented in the year of 1962. So the inventors are G.M. Anderson and Welsky and E.M. Landis. So they have invented the one tree, then they have given the name as AVL. From their names they have taken the letters that is A, V and L. From their names they have renamed the tree name as AVL tree. Now the full form of AVL tree is Anderson, Welsky and Landis, and here the AVL tree will follow one data structure. While inserting and deleting the elements in the data structure, it will follow the non-linear data structure. Why we are telling it as a non-linear means while inserting and deleting we will not follow any order. That's why the AVL tree is a non-linear data structure, and AVL tree will follow the binary search tree properties. So what are the binary search tree properties means the left subtree is must and should be less than the root element, and the right subtree is must and should be greater than or equals to the root element. So here after inserting the every element in the AVL tree, next we will calculate the balance factor for each and every node in the AVL tree. The balance factor must and should be -1 or 0 or +1. So now we can say what is the formula for balance factor. So here the balance factor is equals to height of the left subtree minus height of the right subtree. So that is denoted by BF is equals to TL minus TR. So the every node must and should be either -1 or 0 or +1 balance factor. So here after inserting the elements, then we will calculate the balance factor in the AVL tree. Now for that one, for calculating the balance factor reason, we are telling it as the AVL tree is a self-balanced binary search tree. So the other name for the AVL tree is self-balanced binary search tree, and it is also called as height balanced binary search tree. So here if the balance factor of any node is +1, it means that the left subtree is one level higher than the right subtree. And next, if the balance factor of any node is 0, then that means that the height of the left subtree and the height of the right subtree both are equal. Then if the balance factor is -1, means here the left subtree level is lower than the right subtree level. So like this we can calculate the balance factor. The balance factor is equals to height of the left subtree minus height of the right subtree. If it is 1, the left subtree have a one level higher than the right subtree. If it is equals to 0, means both left subtree and right subtree have a same level. Next, if the height of the balance factor is -1, means the left subtree is lower than the right subtree. Now here we will see how we can calculate the levels. So here you can see the example tree. 100 is the root element. Why we are calling it as the root element means in any tree the first node which starts the tree is called root element. The level of the root element is 0. Now next we can see it have two children, so that is 50 and 150. The level is level 1. Next 50 have a children and 150 also have a children. So here that is 25, 75, 125 and 175. These four nodes are in the level 2. next 75 have children, so that is 65 and 85. These two children are in the level 3. Like this we have to see the levels of the tree. From the levels only we can calculate the balance factor. Now we can see how to calculate the balance factor for the nodes. First, here in this tree, the which nodes will be at the high level of your tree, those nodes are called as external node, or maybe a terminal node, or maybe a leaf nodes. Here the external nodes are, here I am calculating the balance factor for the 25 node. Here you can see the 25 have a no children, means left children is not there, right children is also not there. So balance factor is equals to height of the left subtree minus height of the right subtree. There are, first we will write the left child is not there, so we have to write it as 0 minus right side children is not there, so we have to take it as a minus 0. 0 minus 0 is equals to the 0. The balance factor is 0. Now next external node is 65. 65 have no children, so balance factor equals to height of the left subtree minus height of the right subtree. So here there is no children, means the left height of the child is 0 minus right child of is also 0, so there is no height for them, so 0 minus 0 equal to 0. And next we have to calculate 85. So 85 also external node, so external node means there is no children for it, so 85 balance factor is 0 minus 0, that is 0. Next 125 is also external node, there is no children, so balance factor is equal to 0 minus 0, that is 0. And next node is 175 is also external node, and it is also a terminal node, and the balance factor is 0. Now next we are going to calculate the next level, that is level you can see here. Here next we have to calculate the 75 balance factor. So BF is equal to, here one child is there left side, so we have to take the height of the left subtree is 1 and minus, and it have a right child also, so height of the right subtree is 1 node is there, so that's why that is 1, and balance factor is 1 minus 1 is equals to 0. Next we are going to calculate the balance factor for 150 node. So 150 have a two children, those are right and left, that is right is 175 and left is 125. Now BF is equals to, left side node is there, so one node is there, that means one level is there, 1 minus right side also node is there, 1 minus 1, so that is balance factor is 0. Now we have to calculate the height of the left subtree, that is BF is equals to, how many levels are there here, only one level is there, so 1 minus, and right side there are two levels, that is here one level and this is also one level, two levels are there. These left and right for the 75 we can consider it as a one level, so one level, then this one is also one level, that is 2, so balance factor is equal to 1 minus 2, that we will get minus 1. Now we have to calculate the balance factor of the root element, that is 100. So now the BF is equals to, see here the left, there the two children are there, left side is there, right side is there, so first we have to see left side, one level is there, 1 2, this the 25 and 75 are in the one level, so that's why first one level, next 2 level 2, and 75 also have a children, that the levels are 3. Now we can consider it as the 1 2 level and 3 level. So BF is equal to height of the left subtree, that is 3 minus, And next we are going to calculate the height of the right side. So here one level is there, 1 and 175 and 125 both are in the one level. So they are the levels are, this is one level and this is next level. So 3 minus 2, our balance factor is 1. So here the balance factor of every node is either 0 or 1 or minus 1. Then we can say this is a balanced binary search tree, or we can call it as a AVL tree. Like this we have to calculate the balance factor, and while constructing the tree also, so we have to take the properties of binary search tree and then we have to construct the AVL tree. Now the small difference between the AVL tree and binary search tree means, while we are constructing the binary tree, we just follow the properties of binary search tree. That is, left child must run should be less than and right child must run should be greater than or equal to the root element. And here while constructing the AVL tree, we will follow the same properties. After insertion or deletion, we have to calculate the balance factor for the every node in the AVL tree. That is only the difference between the AVL tree and binary search tree. Thank you for watching, everyone.